Hi everyone. In this lecture, I'm going to go over the data analysis for the consolidation test. So there is an Excel spreadsheet that you can find on Canvas, and it looks like this. Let me maximize this. Okay, so now if you look at this bottom, we have multiple sheets here. The first one is where you are going to do all your analysis to get the graph for the weight ratio versus log of the pressure or log of effective stress. The other sheets are going to be your loading steps and your unloading and reloading steps. So we have these P's are basically the effective stress or basically the pressure on top of the soil, and that's 0.16, and the unit is kilograms per centimeter squared. So that's going to be 0.16, 0.32, 0.63, 1.26, 2.53, 5.05. So these 1, 2, 3, 4, 5, 6, we have 6 loading steps. So that part gives you the branch that you are doing the loading. Then we have from 5.05, we go to 1.26, which we see the load is decreasing, and that's the unloading part, which your soil starts to swell, and that gives you the unloading branch on the curve. And then after that, you increase the load, and that would be 2.53. Let's see how many more we have, and 5.05 and 10.10. So as you can see, we have 2.3, 5, 10, and also 20. So we have 4 reloading steps. Let me go here. So these are the reloads, 505, 10, or 2.53, 505, 10.1, and 20.21. Okay, so what do we have in each of these loaded steps? That's the data that you read when you are doing the experiment. So this is the time in minutes, and this is the dial reading. The dial reading is basically your displacement. So first it's 0, and then it gets 0.06, which means your soil compacted for 0.06. That's the delta H, the change in the height of the soil specimen. And as you can see here, after 4 minutes, this reading didn't change, so we stopped the test. You don't have to go to 60 minutes. Whenever this displacement is not changing anymore, you can, after a couple of minutes, stop the test and increase the load. So why do we need this? Because you want to find the coefficient of consolidation C sub V. So this is the one that you have to use the square root of time t for. So you're going to calculate square root of time, which is the square root of this column, and then you plot this on a curve like this. This is your displacement, and this is the square root of time t. And then you use the method that we have for square root of time to find C sub V. And for that, I asked you guys to go back to your lectures for the soil class, and if you and also it's in your textbook. I also explained it in the video. I didn't go in details, but let me share you one more time and show you guys how that works. Just to, okay, so that's what I'm talking about, this curve here. So this is the deformation. This is the square root of time. Then you plot this curve. Then you find this line parallel, like tangent to the curve. This OB is x, then you calculate 1.15 times x, then you find this point C, and from there you draw this line to get to the same point that reaches this point A. And then the intercept, if you find the corresponding x value to that, that's the square root of T90. And then if you find T90 from that, you put it here. This is the constant that we have here, and then you have the height of the drainage squared. And I'm going to talk about this height of the drainage when we get, that's the height of the soil, and that's when we get to the Excel spreadsheet. Okay, so that's what you need to do for the first 2 time steps only to find the coefficient of consolidation. Okay, let's go back here. So for this one and this one, you need to do the square root of time t. For the other one, you don't need to do that. Then let's see how we can use all this data to plot the curve here. As you can see, we have different rows here. You can calculate, if you want to have the pressure in tons per square square foot, you can use here this conversion factor here and create this column. Then we have a column for initial reading. So first initial reading is 0. This comes from here. For this particular loading, what is the final reading? You just find it from this first sheet here. So that's going to be the initial reading. That's going to be the last reading or final reading for the first one, okay? And you put it here. Then for the second one, you go to the second load step. This is the initial reading. This is the final reading. You put it here and here. For the third one, this one, you go to the third one. This is the initial reading. This is the final reading. As you can see, the initial reading for this time step is the final reading for the previous time step, right? So the initial reading for second time step is second load step. It's the final reading for the first load step. Then this is for this column and this column. Then for delta H is the change in the height of the specimen, like how much soil got contracted or it got changed in the height. So this is going to be the subtraction between the initial reading and final reading. Then your initial height is the height that you start with, and the initial height of the specimen was 2 centimeters. But you remember that when you're calculating the initial height for the second load step, then you have to go with the initial, so the initial height is going to change. So for instance, here we have this one is going to be the initial height would be the initial height of the specimen minus the height, change in the height that it happened in the first load step. So you're starting with a smaller height. And basically, this is the same as let's see, what is this one? Okay, so pay attention. Okay, I made a mistake here because what? The unit here is centimeters, the unit here is millimeters, so it is important. So as you can see, if you want to find the final height of the specimen, which would be the initial height for the next load step, then you have to divide this one by 10, and that's simply because you're converting the centimeters to millimeters. And then this one, the initial height for the next load step, is simply the final height for the previous load step, right? And so on. Then the average height is going to be the average of initial height and final height divided by, or the average of it, which is the sum of these two divided by 2. Then if you want to find the height of solid, because you want to find the void ratio, the equation we have for void ratio is the height of the solid or height of the void divided by height of the solid, right? So if I divide this one divided by this. How to find them? Height of the solid can be found from this equation, and height of the void can be found by subtracting the total height of the specimen minus the height of the solid, because we know that solid plus a void gives you the total height of the specimen. So you have the total height of the specimen, you have height of the solid, the height of the void is going to be the subtraction of those two. And then the void ratio is going to be the height of void divided by the height of the solid. So let's go over the height of the solid one more time. That's the mass of solid, which we already have it somewhere. Here, that's the mass of the soil, the sample that we had, then divided by A, and divided by G sub S. G sub S we assume 2.7, and also rho of water, which is 1 in this unit, grams per cubic centimeter. And A should be in our lecture. Let me open the actual handout for this experiment. Okay. A is the area of the specimen. Okay, so area of the specimen. Let's go back here. We should have the area of the specimen somewhere, and that's going to be, oh, here we have the sample diameter, so you can find the A, which is the area of the specimen. Okay. Which you can find it from the sample diameter. Okay, so when you find the height of the solid, then you can find height of the void from that, then you can find void ratio, and then you drag it down for all the steps. After you obviously have these two, the rest is going to be calculated from this information, so you can just drag them down. And then you plot the void ratio, which is this column, versus pressure in tons per square foot, which is this column, and that gives you the column, the curve here. The curve that you are getting should look like something like this. Something like this. So you're going to have 3 branches, one loading, one unloading, and one reloading. Okay, so awesome. So this is what you do in this main page. And then for the first and second load steps, you are going to find the C sub B, which is the coefficient of consolidation. And you have to use the square root of time method for that. Okay, so please do this. And you can, I put it also here, T90 and C sub B, and that would be only for these 2 time steps. So only for these 2. I'm just gonna add a border for that. Only these 2. You don't have to go down all the way. So please do the calculations and let me know if you have any questions. I'll be available to talk with over the Zoom or over the email if you have any questions or problem finding any of these graphs and finding the parameters that we need to calculate the settlement. Thank you for your attention. Have a good rest of the day.